In this video, I introduce polar coordinates. Fix a point in the plane. From that point, create a ray called the polar axis. The point will be called the pole. Now this ray will create the positive direction for a real line. What I want you to do is to take that real line and rotate it. The rotation will go counterclockwise to be positive angles. We'll call that rotation theta. If you want to rotate clockwise, the angle will just be negative. Then once you've done so, stop, and then on that number line there is a directed distance from the pole to a place on that line. That will then create a point on that line. So every point then in the plane would then have a coordinate system based upon the rotation of the angle and the directed distance from the pole. Let's plot the point 2, pi 3 in polar coordinates. Now the polar ray creates a positive direction. It's a 1/2 of a line. Pi 3 means we rotate that line counterclockwise through an angle of pi 3 radians, as I've done here in the picture. Then along that line there is a directed distance of 2 units away from the pole. I've plotted the point for you in black. Now notice though that if you wanted to, you could, instead of going counterclockwise pi 3, you can go counterclockwise pi 3 and then an additional 2 pi radians, and the line would be right back where it was and the positive direction has not changed. So this could also be the point 2, pi 3 plus 2 pi. You could also first go a rotation of pi 3 and then add a negative 2 pi going clockwise, going backwards, but the end result would be is that the line would be in the exact same position with the exact same positive direction. So you would have that the point would have the same directed distance from the origin, and the point could then be called 2, pi 3 minus 2 pi. So notice that this point then has at least 3 different representations. In fact, it has an infinite number, because you can add 2 pi or subtract 2 pi as many times as you want from the angle, as long as you don't change the radius, and you'd get a new representation of the exact same point. We represent that as I have here, that the point r, theta in polar coordinates is the same point as r, theta plus or minus really any multiple of 2 pi you like. But our point 2, pi 3 in polar coordinates has other representations still. I've plotted the exact same point on our polar graph paper, but that has the exact same coordinates, or at least it's the same point as -2, pi 3 plus pi. To see why, start at the polar axis, go through a rotation of pi 3. That would then be, this would now be the positive direction. But if you add pi, now this would be positive direction. Remember, this is the number line, so this is the positive direction, so then this would be the negative direction. Therefore this would be a -2 distance from the pole relative to this line. So the point would be -2, pi 3 plus pi. This implies that every single point in polar coordinates has yet another representation. If the point is r, theta, another representation is to change the radius to its opposite, and you can add or subtract pi, or actually any odd number of pi, and this would be correct. Let's go ahead and draw some regions. Let's look at all the points where r equals 2. Now if you think about polar coordinates, there's 2 different actions. You can change the r, you can change the theta. If you change theta, that corresponds to rotating the polar ray. So the point would kind of go around the point, around the pole. But if you change the radius, then you go away from or towards the pole. Just remember that as you try to draw these things. So if r is always 2, that means that the angle can change. So the point, which is 2 units away, can freely rotate around the pole. Well, that means that it must be a circle, and that would be of radius 2. On the other hand, if the angle is pi 3, that would mean then that the line has been rotated to a fixed position, a fixed slope. But the radius can be anything, and remember the radius can be positive or negative. So this then has to be a line. It's a line going to the origin, where this angle here is pi over 3. For the very last one, here if you want all the points where the radius is between 1 and 3, and the angle is from negative pi over 4 to pi, if you look at the polar graph paper, so then let's say this is 1, 2, 3, 1, 2, 3, 1, 2, 3, marking off different distances along the polar axis once the line was rotated. The angle is from negative pi over 4. This would be right here along this line, up to pi, that would be this line. So the region is actually in between this because it rotates this way. But the radius is 1 or 3, so it's from this circle to this circle. So then the region must be what's in between it. It's kind of like a part of a donut, like it was taking a bite out of right here. And that's it. That would be the graph. Now if you want, you can use the normal Cartesian coordinate system and the origin for that system, that's where you put the pole. And then along the positive x-axis, that's where you put the polar ray. From there you just rotate like always. Because of that, and because of some trig, if you describe a point in polar coordinates r comma theta, and look at the same point in rectangular coordinates, Cartesian coordinates, x comma y, there's a relationship between the x, the y, the r, and the theta, which you can probably guess. Looking at this right triangle that would be formed, you can get these relationships between x and y, r and theta, just by looking at that right triangle and using the Pythagorean theorem, or using that the opposite side over the adjacent, the hypotenuse would then be the sine of the angle. The tangent of the angle would be the opposite over the adjacent side, and so on. With these equations, you can then convert points from one form to another. So to be clear, we'll go polar or circular coordinates to rectangular or Cartesian coordinates. So suppose you have a point in polar coordinates. I want to go to rectangular, Cartesian. To do so, we know now that r is 4 and that theta is pi over 4 for the point in polar form 4 comma pi over 4. I need some way to figure out what is x and what is y. So out of these equations, there's only two though that say x equals and y equals, so we should certainly use those. So x then would be 4 times the cosine of pi over 4, and y would be 4 times the sine of pi over 4. So this would then be 4 times the square root of 2 over 2, which is just 2 square roots of 2, and this would be 4 times the square root of 2 over 2, which is 2 square roots of 2. So the point in Cartesian coordinates, rectangular coordinates, would be 2 square roots of 2 comma 2 square roots of 2. That's that one. Now if I want to go from rectangular to polar, I know then in rectangular form, Cartesian coordinates, that x here is 1 and the y would be negative 2. I want one of the equations that says theta equals or r equals, and unfortunately we don't have that. But we do have the tangent of theta equals something in x and y, and we have r equals in terms of x and y. But each of these equations, if I were to solve them for theta or to solve for r, there's many answers, which makes sense because there's an infinite number of representations for the point in polar form. So there should be an infinite number of answers. But we have to find the right answers. So normally what I suggest students do is they just find the angle first, and then from there we'll figure out the radius later, and we'll make sure the radius is correct, either positive or negative, based upon the quadrant it's in. So for example, we know that the tangent of this angle is then the y, negative 2, over the x, and that's negative 2. So theta, one such angle, is then the inverse tangent of negative 2. So that would then be an angle that is in quadrant 4. And it's a negative angle. But our point is in quadrant 4. So since it is in quadrant 4, when I go about finding the radius squared is being equal to x squared plus y squared, that would then be 1 squared plus negative 2 squared. So the r squared is just 5. That means r is plus or minus the square root of 5. I have to pick the correct one. Remember that right now my angle is pointing into the fourth quadrant, and that's where the point is. So then I'm already pointing in the correct direction. I'll use the radius as positive. So the angle could be, the point in polar coordinates could be square root of 5 comma the inverse tangent of negative 2. And that's one answer. That's one way to write it. And of course there's other equivalent forms. For the last few things, you should know how to do some very basic graphs. More importantly, if I give you an equation in polar form, that you can turn it back into rectangular form and vice versa. So let's just try a few of those. Let's go and convert this equation in polar form into rectangular form. So r equals 3. You look at the expressions I have that convert from r's and thetas back into x and y's. So I want to find these things to appear in my equations. Once they do, I just replace them. I notice that if r equals 3, then by squaring both sides, I get r squared equals 9. But I know that r squared is x squared plus y squared, and that's 9. So that's a circle. It's a circle of radius 3, like I've drawn here in the picture. Once again, let's go and convert this polar equation into rectangular form using Cartesian coordinates. So I want an equation in x and y. Well, I want to use the same basic idea. I want to have these expressions to appear somehow in the equation, because if I can make them appear, I know exactly what they're equal to. Well, I have that theta is equal to pi over 6. So I can do anything I want really to both sides. So instead of squaring, I'll take the tangent of both sides. We all know the tangent of pi over 6 is the square root of 3 over 3. But we know the tangent of theta is y over x. So that gives us this, that y equals the square root of 3 over 3 times x. It's the equation of a line. That's all it is. And I've drawn in the line for you. Try that again. Once again, I'd like to know, what is this equation in polar coordinates in terms of rectangular ones, Cartesian coordinates, in terms of x and y's. So to do so, notice that I want to try to have these things appear somehow. So to do so, I can get rid of that cosecant. I think a cosecant is 1 over sine. So I'll just multiply both sides by sine to get r times the sine of theta is equal to negative 2. But we know what r sine of theta is. It's just y. So that's y equals negative 2. So this is the equation of a horizontal line. Last example of this kind. Once again, let's just convert this over into an equation in Cartesian coordinates, x and y. So here notice that if you just multiply both sides by the denominator, you would get r times the sine of theta minus 2 times the cosine of theta, and that's 1. But that's the same as writing r times the sine of theta minus 2 times r cosine of theta minus is equal to 1. But r sine of theta, that's y. R cosine of theta, that's an x. And that's the equation. So this must be the equation of the line, y equals 2x plus 1. Now for more complicated problems like this one here, going and trying to convert this over into an equation in Cartesian coordinates won't be useful, because the equation you get is not something you recognize, so you won't be able to graph it anyway. Here though, notice it's r is a function of theta, so we'll use the same kind of idea as we did with Cartesian coordinates. We'll just pretend that theta is an independent variable and the r is the dependent variable. So for each choice of theta, we'll get a radius, we'll get a point. So we'll just make a list of angles, we'll get a corresponding list of radii, and we'll just plot all those points. And then think of it as if you plot them in order. So as the angle increases, that means then you're going counterclockwise. As the angle increases, as you go counterclockwise, you must go through this point, then this one, then this one, then this one, then this one, and so on. Now you have to then guess what the graph looks like from here. Obviously, it's not something you recognize, but we can guess that the curve looks sort of like this. Now what the other half is, we don't know. We'd have to guess what that looks like too. But if you were to plot more points, it would look kind of like this. Now obviously, it could be done a lot better than I just drew. But that's the general shape of it. And that gives you a basic introduction to polar coordinates. I also went and showed you how to go and convert from one type of equation to another. And I gave you a very simple interpretation of graphs of polar equations also. Next time I'll go more in depth on how to graph polar equations, and then afterwards we'll get into the connection between how we use calculus in terms of polar coordinates.